Hello. Now let us continue. In the last lecture, we will find out the total of the energy of the electron in the Bohr's stationary orbit, and it is given by this relation. When we put the values of the constant, then it comes out to be 13.6 electron volt. So the net relation is this one, where n is the orbital number in hydrogen atom and Z is the atomic number. For the ground state of the hydrogen atom, the energy is minus 13.6 electron volt. So the minimum energy required to remove the electron from the ground state of the hydrogen atom is 13.6 electron volt, and it is called the ionization energy. Now, how can we find out the frequency of the electron in the Bohr's orbit? You know very well that the velocity is equal to distance upon time. The distance covered in one circle or in one round by the electron is equal to the circumference of the orbit, and the time is equal to the time period. So T is equal to 2 pi r upon V. Just put the values of r and V, and we get the expression for the time period. And the reciprocal of the time period is frequency. So the relation we get for the frequency is kZe square into NHR. Now let us move forward. And here now we have to find out the wavelength of the emitted radiation. As you know, according to the Bohr's postulate, the energy emitted in jumping the electron from one orbit to the other orbit is equal to h nu, which is equal to the energy difference of the initial level and the final level. As you know that it is equal to minus 13.6 z square upon ni square minus 13.6 upon nf square into z square. Taking common, the relationship becomes nf square minus 1 upon ni square. Nu can be written as C upon lambda. So 1 upon lambda equals to 13.6 z square upon h into C, and 1 upon nf square minus 1 upon ni square. This is a constant factor and it is equal to the r. This r is called Rydberg constant. And its value is constant, which is equal to 1.01 into 10 to the power 7 per meter. The reciprocal of this wavelength can be represented as a wave number, and it is equal to Rz square 1 upon Nf square minus 1 upon Ni square. Now let us talk about the spectral series. Whenever the electron jumps from higher energy level to lower energy level, the photon is emitted. Whenever it jumps from the orbits 2, 3 and 4 to the first orbit, the series is a Lyman series is produced. This series lies in the ultraviolet region. So we can find out the wave number or the wavelength by using this relation for the Lyman series. Similarly, when the electron jumps from the third, fourth and fifth orbit to the second orbit, then the series produced is a Balmer series which lies in the visible region, and using this relation we can find out the Balmer series. When the electron jumps from 4, 5 and 6 orbit to the third orbit, then the series produced is a Paschen series, which lies in the infrared region, and from these formulas one can find out the wavelength for the Paschen series. When it jumps from the 5, 6 and orbit to the 4th orbit, the bracket series is produced, and similarly when it jumps from the 6th and 7th orbit to the 5th orbit, then the Paffin series is produced, and both the series lies in the infrared region, and we will use this formula for the bracket series and this formula for the Paffin series. It is an energy level diagram. Now see, in the case of the Lyman series, the electron jumps from the second orbit, third orbit, fourth orbit, fifth, sixth and so on to the first orbit. In Balmer series, the electron jumps from the third, fourth, fifth, sixth, seventh to the second orbit. In Paschen, the electron jumps from the fourth, fifth and sixth to the third orbit and so on. It is an energy level diagram which represents the total energies of the electron in different stationary orbits of the atom is an energy level diagram. Now the excitation energy, excitation potential, ionization energy and the ionization potential. As you already know about the excitation energy and the ionization energy, you have studied about it in chemistry. Excitation energy is the minimum energy required to excite the atom from the ground state to the higher energy state. So in case of the hydrogen atom, the energy in the ground state is minus 13.6 electron. And in the first excited state, that is at n is equal to 2, it is 3.4 electron volt. So the excitation energy is 10.2 electron volt. That whenever electron jumps this amount of the energy, it jumps from the first level to the second level. Excitation potential is the minimum potential required for an electron so that it gets sufficient energy to jump from the ground state to the higher state. So the minimum potential required by the electron to jump from the first level to the second level is 10.2 volt and is called excitation potential. Similarly, the ionization energy is the energy required to ionize the electron, and the ionization potential is the minimum potential required by an electron so that it may go or it removes from the atom is called ionization potential. For the ground state of the hydrogen atom, the ionization potential is 13.6 volt. For the first excited state of the hydrogen atom, the ionization potential is 3.4 volt and so on. Now the limitations of the Bohr model. The Bohr model is applicable to the hydrogen atoms only. It cannot be extended even to the 2 or electron atoms, that is for the helium nuclei. Difficulty lies in the fact that each electron interacts not only with the positively charged nucleus but also with other electrons. While the Bohr's model correctly predicts the frequencies of the light emitted by the hydrogenic atoms, but it is unable to explain the relative intensities of the frequencies in the spectrum. Thank you and have a nice day.